All right, so we're going to continue talking about limits and the correct notation. The big difference is now we're going to be talking about the graphical approach to it and something called a one-sided limit, which has to do with what we were talking about with pluses and minuses earlier today. So graphical approach to this and the one-sided limit. All right. So a one-sided limit is when you approach a number from both the left and the right side. And so a right-handed limit is denoted as approaching C+. That means we're graphically approaching from the right-hand side as a direction. And then the left hand is denoted with a C-, and that means that we're approaching from the left side. Okay, so we'll have something coming in from the right and something coming in from the left and coming towards the same number, hopefully coming towards the same number. That's called a one-sided limit. So as you read that, you don't say C+ and C-, you say approaching C from the right or approaching C from the left. All right, so here's some pictures of a graph and how that might look. If you're approaching a value from the left, that means I'm following the function and I'm heading towards that open circle from the left-hand side. So I'm sort of creeping up the slope and following it up from the left. If I'm approaching it from the right, I'm going to be coming down that way. But those two things are both approaching the same hole. The next picture, it's the same idea. Okay, approaching from the left, approaching from the right. Okay, or you could even draw it like this. Approaching from the left, I'm coming to that way. Approaching from the right, I'll be coming from that direction, but I'm still approaching the same hole. It is irrelevant that there's this little floater down here. Okay, that floater is there almost like a distractor. It's meant to, distract you from your focus is on what you're approaching, not what the actual little floater is. And then in the last picture, it happens to be approaching a closed circle, so approaching from the right, approaching from the left, and they're approaching that closed hole. So visually, that's what we're talking about. This next example is an example of a hyperbola. And in this hyperbola, we are asked to approach 0. And so your job is to do both sides of the hyperbola. So you want to approach from the left of 5/x. The left side of 0 is following the branch of the hyperbola that is heading down towards infinity. It's taking a nosedive and just hitting that asymptote and just heading straight down. And so we say that the left, approaching 0 from the left-hand side, is going to be negative infinity. The right one, I'll do in a different color, the limit approaching 0 from the right side. That one we would be following the upper branch and approaching from the right. We're hitting that asymptote now, but we're skidding towards positive infinity. And so the answer to this is positive infinity. So these are the one-sided limits, and they're different values. The value approaching from the left was different than the value approaching from the right. So the limit itself does not exist because the left-hand value of the limit and the right-hand value of the limit are two different numbers. Here's another graph. We can approach different values from the left and the right. We can approach 0 only from one side. Okay, unmute yourself. Which side can we approach 0 from?
From the right side.
Only from the right side because there's nothing even drawn on the left. So we can approach 0 from the right side. So we say 0 plus of that function. And we would be approaching 0. You would approach the origin. We can approach 2, but we can only approach 2 from one side because there's nothing graphed on 2 on the other side. We can only approach 2 from the left. And as we approach 2 from the left, we're approaching an open hole. And again, the fact that it's open and not filled in is irrelevant because we don't care whether it's open or closed. We just care that we're getting close to it and we're getting close to the number 4. And then the value at 3, we can only approach from the right because there is nothing on the other side of 3. And so we approach that from the right. That's approaching the x-axis, and so that approaches 0. So again, these are all called one-sided limits. So then that leads us to the concept of a two-sided limit. A two-sided limit would be when the left side and the right side are the same. Okay, when the left hand limit and the right hand limit all approach the same number, and then we say the limit exists. And that is called a two-sided limit. Okay, so here you've got your right, and here you have your left, and they are all equal to the same number. Okay, so we want to check some two-sided limits here. I'm going to check a two-sided limit at the number 1, and I'm going to check a two-sided limit at the number 3. I am not going to check a limit at the number -2 because the number -2 would only be a one-sided limit because it only has, it's only a part of one of the inequalities. So we want to check both of the limits, both two-sided limits here. So let's check the limit as x approaches 1 from the left of f of x. And let's check the limit as x approaches 1 from the right of f of x and see if these two-sided limits match each other. So if I'm approaching 1 from the left, I'm going to be using x plus 2 as my function. So I will be plugging in 1 into that. So 1 plus 2 is 3. When I'm checking 1 from the right, I drop down to the middle piece of the function, and that gives me a value of -1. So my conclusion here is because the two-sided limits don't match each other, then we would say the limit as x approaches 1, like as a whole, 1 as itself, 1 with not a plus or a minus, but just 1, does not exist, DNE. In order for the limit approaching 1 to exist, then the limit approaching from the left and the right have to be the same. The two-sided limits need to match. So let's try the same thing at 3. Let's check the limit as x approaches 3 from the left of the function, and let's check the limit as x approaches 3 from the right of the function. Approaching from the left, I'll be using the middle value, so that would be -1. Approaching from the right, I'll use the lower piece of the last piece of the function. So that would be -3 plugged in plus 2. That is also -1. So here's an example where the two-sided limits do equal each other. So then we can conclude that the limit approaching 3 overall is equal to -1 because the two-sided limits matched each other. All right, last one. Graphically here, we are going to check two-sided limits at the points of connection. So we're going to check it at 0 and we're going to prove it at 1. So we'll do both. So I'm going to put a a red dot at 0, and I'm going to prove the one-sided, that the two-sided limits there match each other. So I'm going to write approaching 1 from the left, and I'm going to compare it to the right, and then I'm going to conclude what I can conclude overall about approaching 0 overall. So approaching from the left, I approach the origin, which is 0. Approaching from the right, I approach the origin, which is 0. And so the limit 0 overall is 0. And then the other junction point would be the number 1, and you do the same thing. A formalized proof, if they say prove your answer, justify your answer, this is the 3-step process that you show. You just clearly show, state the left-hand limit, the right-hand limit, and then the overall limit. And so if you're asked to do that, you say, I'm going to check the one-sided limit from the left, I'm going to check the one-side limit from the right, and then I'm going to make a conclusion about the overall limit once I've done the first 2 things. And in this case, the left-hand limit was approaching a y value of 1, the right-hand limit is approaching a y value of 1, therefore the overall limit approaches the value of 1. So if they're different, then you say D and E for the 3rd step. If they're the same, then you have proven a two-sided limit.